started first. If anybody tried to see me earlier today when I was supposed to have office hours, I apologize. I got into a meeting this morning and I finally had to walk out in order to get here in time for lecture. I just couldn't get them to stop. So. Anyway, we're now going to move through the electromagnetic properties of materials. There we'll talk about electrical conductors, then magnetic materials, then photonic materials, or materials that are used for their optical properties. All three of these classes of properties have to do with the response of materials to electromagnetic fields or electromagnetic waves. So they all kind of fit in together, as you'll see. We begin with electrical conductors. Now, if you go to a good solid-state physics book, you'll find that physicists really distinguish, well, three kinds of conductors. The old-fashioned classic physics books will distinguish metals, which conduct electrons, and insulators, which are dielectrics, which ideally do not. Getting thrown into the mix in more modern physics are superconductors, and as we'll see when we briefly talk about superconductors, a superconductor, of course, conducts electricity, but it's not just a good metal, it's a completely different kind of beast. So we'll talk about those. Semiconductors, which are technologically important, fit counted in the credits between metals and insulators. They conduct electricity, but they conduct poorly, and their poor conduction of electricity is actually used in making microelectronic devices. Magnetic materials, of course, are the materials that respond to magnetic fields. Of the various types of magnetic response, the only one that has really important commercial applications is ferromagnetism, so we'll talk about that. Finally, we have photonic materials, materials that respond to light. These have always been important materials. We have windows, for example, that let the sun in. But in recent years, they have become extremely important because of the use of light to do things like transmit information over optical fibers, to produce light through various electronic processes that give us LEDs and lasers and things of that sort. So in recent years, optical properties of materials have really emerged as an important area of material science. I'll make a point of talking about this. Okay, let's begin with electrical conductors. And the beginning thing to know, which you all know already, is just Ohm's law. If you put a voltage onto a material, a potential difference, in response there will be a current, and the voltage is equal to the current times the resistance of the material. Now we of course are interested in material properties, and it's important to recognize that, like some other examples we've already seen, Ohm's law does not give us a material property. The reason is that what kind of looks like a material property, this resistance, is an amalgam of material properties and purely geometric properties. So in order to talk about the material science of conductors, we've got to rearrange this law so we get the geometry out of the equation and settle in focused on the material property. We do that by recognizing, first of all, that we need a measure of the current, which is independent of the geometry, and the current would be the current density multiplied by the cross-sectional area. So the current has in it both the current density and the cross-sectional area. The voltage has in it the electric field and the distance. So if we get the geometry out of this equation, it drops into the simple form where we have electric field times distance. Field times distance gives us the voltage drop. Current density and cross-sectional area gives us the current. Here we have the resistance. If we get the geometry out of it, we get the equation in a geometry-independent form. The current density is equal to the conductivity times the electric field. Or flipping it around direct corresponding to Ohm's law, the electric field is the current density multiplied by the resistivity rho. Either the conductivity sigma or its reciprocal, the resistivity rho. These are material properties. And this is the form of Ohm's law that pertains to materials. In fact, we ordinarily, when we're talking about materials, we don't write this. We use the current density is equal to the conductivity times the electric field, because this has precisely the same form as, for example, the equation for heat conduction or diffusion. A flux, in this case the flux of electrons or the electricity, is linearly proportional to the driving force, in this case the electric field, and the constant of proportionality is the material property, which in this case is the conductivity. So this equation, which is the equivalent to Ohm's law, has precisely the same form as Fick's first law of diffusion and Fourier's law of heat conduction. Flux is force multiplied by material property. And so this is the form in which we normally use it. Material properties, well, in general, this equation, like all other flux equations, its form is sensitive to the symmetry of the material. In general, the current flux is a vector. It has a direction as well as a magnitude. Similarly, the electric field is a vector. It has a direction. And the material property that connects two vectors is a second-order tensor. It has, in fact, 9 different components. So, in fact, we can have several different conductivities for the same material. But if we're talking about a material that has cubic symmetry, as do an awful lot of the crystals we've talked about, or isotropic symmetry, as, for example, glass or polygranular material with random orientations of the grains, then in that kind of material, the conductivity is not a tensor but a scalar. It has the same value in all directions. The flux vector and the electric field vector are in the same direction, and we could write the equation in this simple scalar form. Just keep in mind that if, for example, quite frequently these days, if you get involved in microelectronics, you might have conductive films that have hexagonal crystal structures, for example. There you'll have to worry about two conductivities. The conductivity along the axis of the hexagon and the conductivity in the basal plane. So if you get to more complicated symmetries, you have to worry about more complicated vector versions of that law. We're not going to worry about that anymore here. Well, let's begin with conduction by electrons, which is the way we would normally conduct in the metal. And ask ourselves what really happens when we conduct by an electron. Now the equation that we wrote back here is a simple flux equation. It says the diffusion flux, the electron current density, is proportional to the electric field. But you know enough physics, you all do, to know that when you put an electric field on a charge like an electron, you don't get a velocity, you get an acceleration. The charge is accelerated in the electric field. So how do we translate an acceleration into the velocity that's associated with the flux? The flux is just a number of particles multiplied by the velocity. So how do we get from one to another? Well, we do it in the following way. If we look at what really happens when you put an electric field on a material that contains electrons or mobile, the electrons are immediately accelerated by the electric field. But they don't go very far before they run into something. They run into defects in the lattice, they run into phonons, vibrations, they run into one another. And those things that they run into disturb that process. So if you were to take the velocity of an electron that is subjected to an electric field in a real solid and follow the velocity as a function of time, you see something kind of like this. You see the velocity increase, gets a collision, drops down. My pointer's kind of dying here. Increases again, gets a peak, drops down. It would be a very jagged profile as the particle is accelerated, collides, slowed down, accelerated, collides, slowed down, and so on. And from that jagged profile of velocity versus time, we can extract a mean velocity or a drift velocity. Now, I've written that mean velocity of del V because there's another subtlety here that you have to kind of consider, and the complexities that you don't have to worry about too much, let me mention. The electrons in a solid, they already, they're in bands, they already have momentum, they already have velocity, they're moving through the solid with a given velocity. So when we talk about this del V, we're not talking about the total velocity of the electron. We're talking about the incremental velocity over the velocity that we otherwise have just because of the state it's in the solid. So it's the incremental velocity that is changed by the imposition of the electric field. So what's the incremental velocity? Well, the velocity of the electron, the actual velocity, is its velocity in the band plus del V. Del V is equal to the force times time divided by its mass. The force on the electron is minus E times the electron field, E is the electron charge. So Ft over m is the electron charge times the electron field times the time over which the force is applied divided by m. Well, what's the expected value of that del V, the average value over time? Well, the only thing on the right side of this equation that varies is the time over which the force is applied. Because the force is applied for the time basically between collisions, and then it has to start all over again. So if I just replace that time by the average time between collisions, tau, I get that the incremental velocity, the expected value of the incremental velocity, is minus the charge, the electric field, the time between collisions, divided by the effective mass of the electron in it. And this is the equation that you'll see in all of your typical physics books when this kind of phenomenon is discussed. Another way to look at that is instead of talking about the time between collisions, I can talk about the mean free path between collisions. How far does the electron travel between successive collisions? If I call that L, then tau is just the expected value of L over the actual velocity of the electron V. What appears in this equation, this V, is not the incremental velocity, this is the basic velocity of the electron. So I can write this as EE tau over m, or EEL divided by mv. And those are the two equations. Well, the drift velocity, if you look at this equation, is linearly proportional to the strength of the electric field. I have e to the first power on this side of the equation. So I can write that the incremental velocity is minus mu e, where mu is called the mobility of an electron, and that's equal to E tau over m, or EL over mv, the mean momentum of the electron. And this is the electron mobility. The electric current, the net current going in a particular direction, we have the velocity of the electron in the background. But if there's no electric field, the electrons are equally likely to be moving in all directions. So that V, the mean speed of an electron in the band structure, in the lattice, carries no current at all. The only thing that gives us current is the del V, the increment of the velocity, which is always in the same direction because it's in the direction that the electron is driven by the electric field. So if I want to know the electric current, that would be N times E. N is the number of electrons per unit volume, number of conduction electrons. E is the charge per electron. Del V is the effective velocity, the drift velocity, the velocity with which the electrons are moving. And that will give us the current flux, J, the current density, NE del V, or NE times the mobility times the electric field. So this is how we get Ohm's law. The current density is linearly proportional to the electric field. The modifier, which is a material property, is the density of conduction electrons multiplied by the electron charge multiplied by the mobility in the electric field. And that gives us an equation which is a very important one in understanding of electrical conductivity in materials. The conductivity sigma is equal to N times E times mu. The number of carriers, charge in the carrier, mobility in the electric field. Well, if we're talking about conduction by electrons, the charge of the carrier is fixed. So the two things that will vary from material to material and circumstance to circumstance are the density of carriers and the mobility of the carriers through the lattice in the electric field. These are the things that we have to understand. A bit more specifically, I can write that sigma is NE squared tau over m, or NE squared L over mv. The resistivity, which is the reciprocal of sigma, is mv over NE squared L. It's very important, as you'll see in just a minute, that in the resistivity, the mean free path appears in the denominator of the equation. In the conductivity, it appears in the numerator of the equation. Okay? So let's march forward to the next step. The things that we've got to worry about to understand what makes some materials good conductors and others not good conductors are how many electrons are available to move and how fast can they move under the electric field. You remember when we talked about metallic conductivity. When we talked about metallic conductors, we said there were three kinds of basically different metallic conductors. The first kind are natural metals. In all metallic conductors, the Fermi level must lie within a band. It must lie at an energy which is within a continuous range of available states, so that a very slight excitation of the electron can put it into unoccupied states and can cause it to move. But we said there are three kinds of metals. There's what we call a natural metal, in which the Fermi level sits well within a band, just all by itself. There's what we call overlap metals, in which the number of available valence electrons would be sufficient to saturate a band, but that band overlaps with another band. And because of the states available here in the overlap, the Fermi level lies somewhere in the overlap region. The natural metals are things that have odd valence. Copper, silver, gold, aluminum, things without sodium, potassium, all good conductors don't have odd valence. The band overlap metals tend to be things that have even valence. Zinc, calcium, others that magnesium, things of that sort. The third class of metals are the transition metals. The transition metals have partly filled d orbitals in the atom. There are 10 d orbitals in each atom. So in the transition metals, the band that is associated with those d orbitals, which is always rather narrow because those d orbitals end near the nucleus, that band is only partly filled. So the band structure in a transition metal looks something like this. There's a conduction band down here, here's the overlapping d band, and the Fermi level sits inside the d band. And these really are the three different qualitative band structures that we get when we're talking about metals. But which of these are good? It turns out that the natural metals always have high conductivity. This is where your good metals come from. You wire your house with copper or aluminum. You'd be happy to wire it with gold, except somebody would steal your wiring the next day, so that's not a good idea. Silver can save it. But copper, even copper these days has become something of a problem. So I suggest aluminum wiring for making a house. That's why you're getting conductivity, but it needs to stay that a lot. Band overlap metals have lower conductivity, which is kind of surprising because they look like good metals. I'll tell you one in a moment. Transition metals have even lower conductivity, which may be more surprising at all because there are all kinds of electrons. All right, now what's going to determine the conductivity of the metal? The primary thing that's going to determine the conductivity of the metal is how many conduction electrons are available. So let's look at the following. Here is just a plot that shows the number of electrons as a function of energy within a typical band. I don't want to get too fancy with this. It's just a qualitative schematic illustration. Generally, the number of states available for electrons increases with the energy as we go through a band until we get at least past the middle of the band. As a consequence of that, right near the middle of the band, the energy of states is high. In the natural metals, the Fermi level is sitting right here in the middle of the band. Well, now, how many electrons are available to conduct electricity? How many electrons are there? Well, only those electrons that are close to the Fermi level can get excited. These electrons back here may be in the conduction band, but if they're more than kT away from the Fermi level, there's no way they're going to be thermally excited to conduct electricity. You've got density way back here, they may as well just not be participating at all. So the thing that matters when we ask how many electrons are available to conduct is what is the density of states right here at the Fermi level. How many electrons are there that have energies very close to the Fermi level so they can be easily excited and can run through the material? In natural metals, where the Fermi level is right near the middle of the band, that density of states is always very high. How high depends on what metal we're talking about, and copper, silver, and gold have slightly different densities of states at the Fermi level. Aluminum's a little bit lower, but they're all high. So these are all good metals. When we get to the band overlap metals, we get to the problem that the density of states hits a maximum somewhere within the band, then drops off as we get to the top of the band. Just for reasons we don't need to talk about. It's a universal phenomenon. So when we have a band overlap metal, we have the trailing off density of states from the lower energy band overlapping with the initial density of states from the higher energy band, which is also low. So the density of states here in the band overlap region is normally not very high. We're not getting an awful lot of states from the conduction band. We're not getting an awful lot of states from the excited band. So the total number of states from the Fermi level, it's high, but it's lower. So these are not such good metals. So band overlap metals like zinc and magnesium and so on, they're decent conductors, but you wouldn't want to wire your house with them. They're not that good. What happens in the transition metals? Now this is kind of surprising, because in the transition metals, we have a very narrow band. It's got 10 electron states in it. You know, the whole conduction band only has a maximum of 6 states, and it's got 10 in that narrow band. So the density of states near the Fermi level in a transition metal is enormous. So why isn't iron the best conductor of all? Well, remember, the conductivity is a product of two things. How many electrons are there, and how mobile are they? And what happens in the transition metals is while the density of electrons goes shooting up that are available for conduction, their mobility goes straight to pot. The reason that happens is the following. The d levels of these individual atoms are near the core. They're inner. They're not spread out like the valence electrons are. And the net result is that when an electron gets into one of these d levels, it gets trapped, if you want, around the core of the atom and has difficulty separating itself. So when we follow the path of a hypothetical electron running through a transition metal, it could do something like this. My analogy is somebody trying to run a 100-yard dash in a field full of potholes. You can't go very far before you get trapped. As soon as you get shaken loose, you get trapped again. Get shaken loose, you get trapped again, and so on. So there are lots of electrons trying to wiggle their way through this field full of potholes, but they can't run very fast because they keep falling in the holes. The net result is the mobility is low, even though the number of electrons is high, and transition metals are lousy conductors. So there are two things that get into conductivity. The number of electrons that are available to conduct electricity and their mobility. In normal metals and overlap metals, the thing that governs conductivity basically is the number of electrons available. That says what is the density of states at the Fermi level. How many electrons are sitting in energies right near the Fermi level so they can be easily excited to conduct electricity. In transition metals, the problem is mobility, because as the electrons try to move through the lattice, they keep getting trapped in these various atoms, and as a consequence they have difficulty moving. And that basically qualitatively explains what you need to know about metallic conductivity. Resistivity, well, to go a little bit further, of course, even with good metals, the resistivity or the conductivity can vary quite a bit from one to another. If you go into a hardware store and you start looking for copper wire, you will find for sale several different grades of copper wire at different costs. And those different grades of copper wire basically will differ in the purity of the wire. Usually the best stuff is OFHC, oxygen-free high conductivity. But there is the microstructure of the metal does have a significant effect on what its conductivity will be. How is that? Well, that's because, remember that our mobility is governed by scattering within the material. The electron is accelerated, it scatters, accelerated, it scatters, accelerated, it scatters. So what can it scatter from? And that will determine what the resistivity is. It can scatter from several things. One thing it can scatter from are, well, it scatters from imperfections in the lattice. The way we have set up, when you calculate the band structure of a metal, you calculate it, you put the electrons in states that are waves that are calculated to fit the perfect background lattice. So if we imagine we have a perfect crystal, then at zero temperature, so all of the atoms were located precisely where they were supposed to be. And if we could even ignore the 0-point vibrations, then the conductivity, the resistivity would be almost zero. Even then it wouldn't be quite zero because you have to thermally excite electrons to get them into the state, but almost zero. As you come up in temperature, the atoms begin to vibrate. As they vibrate, as the phonons become excited, these are the ion cores. And vibration means that the ion core has moved off the place where it's supposed to be and is slightly displaced. The electron coming along in this ideal state is looking for an ion core right there. But the ion core isn't there, it's up here. And as a consequence, that electron is going to be scattered by that displacement of the ion core. That's what we call phonon scattering. And if you take a decent, particularly graduate level solid physics course, you'll learn how to calculate that. Right now you don't want to. We just need to know that vibrations will scatter electrons, and as a consequence, do contribute to resistivity. Well, any imperfection in the lattice will also do that, because it also has the consequence that the electron is zipping along, it's looking for an atom of type A sitting there. And if there isn't an atom there because of a vacancy or dislocation, or if the atom sitting there is in type A to type B, then the electron is going to say, wait a minute.